Hello everyone. In this tutorial we're going to be covering displacement mapping in Redshift. And so here I have a basic plane and we're going to apply our displacement map. Currently it only has a simple Redshift material. Nothing really particularly special about this. And we have two textures. One is a height map displacement and the other one is a vector displacement. And so we will first start with a height map based displacement. So let's create a displacement node, a Redshift displacement, and we'll plug in our color into the texture map, and the output for our displacement node will plug into our displacement input. And we'll open up the Redshift render view by going up to the Redshift tab and hitting the Redshift render view. Now let's press the play button on the IPR to get the IPR started. And so, as you can see, right now we are missing our displacement even though we connected the texture map. So the reason for this is Redshift also allows you to activate the displacement at the object level. And so if we have our object selected and we go under the Redshift tab, you'll find the options for the tessellation and displacement. So if we activate tessellation and we activate displacement, we'll now see, if you zoom in here, a subtle change. And so if we increase our displacement by either going into the displacement node, or you can increase it here at the object level under displacement scale. Let's increase this to 10. And you'll see that instantly our displacement is affecting our plane. We also have the option to increase the maximum scale, and this allows you to increase beyond the defaults. As you can see, it looks like our displacement's bulging and then flattening out a little bit here. So let's increase our maximum scale at the object level. Let's use 10 also. And now you can see the full influence of our displacement. And that's how you use a height field displacement. What happens if we want to use a vector displacement? Let's try that next. Now let's try using our vector displacement map. So let's generate a new displacement node by hitting tab and typing in displacement, and we'll bring up this Redshift displacement node. We'll plug in our color output into the texture map input, and this time, since we know this is a vector displacement, we'll change it to vector under the map encoding, and the space type, instead of object, we know that this was generated in tangent space. And now that we've done that, let's plug it in, our output, into the displacement shader slot. And as you can see, we have a little bit of a subtle influence. So let's increase the scale. Let's try 10. And now you can see the vector displacement influence. Let's increase it to 25. And now you can see our ear. And so this is how you can go between using regular height field displacement and vector displacement. So what happens if you want to blend between two different displacement types? For that, we have the Redshift Displacement Blender. So now let's use a Redshift Displacement Blender. So again, hitting tab, start typing displacement, and you'll see the Redshift Displacement Blender. And so what this node lets you do is it lets you input multiple displacement maps and blend between them, either using mass or just a blend weight. And you could also have additive mode, which adds together the displacement values. So for this example, let's plug in our ear as the base input. And then we'll plug in our out into the displacement shader slot. So if we do this, nothing's happening because right now we have nothing layered on top. So now let's layer up our mountain shape, our height field displacement, into the displace input 0. And again, nothing's happening just yet because our blend weight is set to 0. So as we increase this, our influence from our mountain will increase until we get all the way to 1, where now it's fully only the mountain. And so this allows you to blend between two displacements. Or you can activate additive mode, where it layers the values on top of each other. And so this is a great way to blend between two completely different displacement maps and displacement map types. You can blend between vector and height field using the displacement blender. Now let's go into a little more detail regarding the displacement object options. So let's go back to our basic mountain and we'll disable our displacement blender. And we'll just stick to our basic displacement of our mountain for now. And we'll cover some of the parameters. So when you click on your object, you go back to the Redshift tab, you have all these parameters regarding displacement and tessellation. And let's see what some of these parameters do. To help us better understand what's going on when we increase or decrease some of these parameters, let's make a Redshift wireframe shader. And so what the Redshift wireframe shader does is it shows us the render time tessellation of objects. So if we plug this in, the out color, into the diffuse color, we'll see, if we zoom in here, our triangles making up our shape. And so this helps us better understand what's going on once we start changing some of the parameters. So let's go back now to our object and start changing some of the maximum subdivision and minimum edge length parameters. If we decrease the maximum subdivisions, we will get less subdivisions inside of our object. So if we decrease this to 2, for example, you will see that now the triangles are much larger. And so you could think of this as your resolution. Less means you have less geometry for the displacement to be working with. So if we increase this now to 8, once again you'll notice the triangle size difference. If you press 6, you'll notice, why is there no change between 6 and 8? And the reason is because of our minimum edge length. This controls how small our tessellation can actually be relative to our screen resolution. And so right now we are using screen space adaptive. And what this does is, relative to how close your camera is to the object, there'll be more tessellation in the objects near compared to the objects that are further away. And so this works by relative screen resolution. So if we decrease our minimum edge length to 1, we'll get much higher resolution fidelity, as you can see. And the reason that 1 is increasing the resolution so drastically is because 1 represents 1 screen pixel that the object can subdivide in, while 4, the default, means every 4 pixels we can have a subdivision. And so if you want to increase your resolution for your displacement map tessellation, you need to not only increase the maximum available subdivisions, but also decrease the minimum edge length that you can subdivide inside of. These same principles apply when using world space tessellation. So if we go here to the screen space adaptive and disable this, what we end up is with displacement tessellation that is equal throughout the object. So now the resolution here is the same as it is further away. One of the great things about using Screen Space Adaptive is that it's very memory efficient. But sometimes your object is getting close to your camera and further away in an animation, and so you might not want the variation in resolution, and you want the object to remain consistent, and that's why you might want to disable Screen Space Adaptive. And so once again, the same applies where you want to decrease the minimum edge length and increase maximum subdivisions. But this time, minimum edge length works by using world space units. So instead of working with pixel values like the Screen Space Adaptive option works, this version works by using world space units. So if we were to go down to 1, it won't change. And the reason is because our asset is already in pretty large world space units. So we have to use values smaller than 1. So let's try 0.5. And now you can see our resolution changed. Let's try 0.1. And now you can see the resolution increased even further. And so this allows you to change the resolution of your object relative to either the distance if you're using Screen Space Adaptive, or across the entire object using world space. Now let's turn back on Screen Space Adaptive and move back to the defaults. And now let's explore another feature. The Redshift render view allows you to pause or freeze the retessellation of your object when using Screen Space Adaptive. So if you change camera angle, for example, it has to always recompute. And so right now, if our asset was heavier, it would have to recompute the tessellation, and that can sometimes slow down the look dev process. So what the Redshift render view allows you to do is by clicking this snowflake icon, you can click this, and this will freeze your tessellation values that you currently have. As you can see, if we zoom in here, you can see the difference. The object closest to us has higher tessellation, while the further it gets from the camera, the larger the tessellation gets. So now that we froze the tessellation, if we go to the back side, for example, and zoom in, you'll notice our tessellation values are much larger. And so this allows you to quickly freeze the tessellation and still use Screen Space Adaptive and continue the look dev process without having to recompute over and over the tessellation as you get closer to the object, which is a great feature for fast iterative look dev. And now another interesting feature is the enable auto bump mapping. And so what this allows you to have is extra detail inside of the displacement without actually creating more displacement or having to use a bump map. So if we disable our wireframe for a second, and let's increase this to a gray value again, and you'll notice that we have this little finer detail in our mountain. What happens if we disable on the object enable auto bump mapping? You'll notice that now we lost all of that finer detail. And so what this lets you do is increase the detail level of your asset without actually increasing the tessellation or subdivisions. And this allows for faster renders while still keeping a lot of the detail. If we were to attempt to keep this level of detail without enabling auto bump mapping, it would require a lot more subdivisions. So let's turn that off and increase our subdivisions to something like 8 and our minimum edge length to maybe 1. And you can see now we brought back this detail, but we also increased heavily, if we turn back on our wireframe, the amount of times we had to subdivide, and the overall geometry increased. Instead, what's typically more efficient is to just enable the auto bump. And as you can see, we brought back in the detail, but without the cost of having to tessellate the object so heavily. And so that's the benefit of using Enable Auto Bump Mapping. Another great feature for optimizing your tessellation and subdivisions is using the out-of-frustum tessellation factor. And so by default, this is set at 4, which is a pretty good average number for most situations. And so what this allows you to do is your tessellation will increase or decrease relative to what's outside of your camera view. So if we were to zoom in, for example, to this other end of our mountain, and we were to refresh our freeze tessellation, so you can see that now our tessellation is pretty high relative to how close we are to this corner of the object. But if we were to zoom out now and go to this other side, which is pretty far from our camera view, you'll notice that this corner has a blending of less and less tessellation. And so what this lets you do is, relative to how far your camera view is, your frustum of your camera, you can actually tell it to decrease the tessellation so that you save on VRAM and tessellation timing. And so what this number lets you do is decrease or increase how aggressive this is. So if we were to increase, let's go back to our original position. And we were to increase this to the maximum of 32. And so what's going to happen is, if we were to go now back to that corner, you'll notice that a lot of this corner now that was out of view of the camera originally has now a very low and lowering tessellation the further away. So it's great because it lets you be more efficient when needed if your camera isn't even viewing this half of the object. And it dynamically decreases to give you a nice fall off on the amount of tessellation that you're giving your object. And so that's what the out-of-frustum tessellation factor does. It allows you to control the tessellation effect occurring outside of your camera's view, which can save in render time and VRAM. Something to also keep in mind is the maximum displacement. And so let's disable our wireframe, and let's just use a shader. And so if we just drop down and we look at this from the side, and we go back to our object displacement parameters, and we kept this at a default of 1, you'll notice that it's flat. And the reason is because we have clamped the maximum height possible that the displacement can influence. So if your displacement requires it to actually poke up a lot, it's usually a good idea not to only increase the displacement scale, but to also increase the maximum displacement. This allows you to give the displacement a little more wiggle room to influence how much it can poke up out of the surface. So keep that in mind when using displacement maps that, like this particular one, lift up off of the surface quite a lot. One more thing to keep in mind when working with displacement is sometimes your displacement will not work correctly in that the black point will not be in negative, pushing down on the object, and the reason this can happen sometimes is relative to the package that your displacement map was created in. So you sometimes have to remap the texture values. This actually occurs when using the redshift noise in some particular cases, or certain noise types, or if your displacement texture came without negative values. So let's say it's an 8-bit or a 16-bit format. Sometimes you have to remap the values. And usually this isn't the case when you're working outside of ZBrush or a dedicated sculpting app, where typically an EXR file can actually support negative values. But in some situations you need to change the ranges. And so what's going on is that black typically represents negative, gray means in the middle, and white means pushing upward. And so here in this example we have the redshift noise, and we have a displacement, and we're going to increase the displacement to 5. And what you'll notice is inside we have these flat zones and areas. And the reason that this is happening is because we have no negative influence. Our black is not pushing downward. And so if we were to look at this sideways, we don't really have any negative influence here. It's just remaining flat. And so what you have to do in these situations when they happen is, under the redshift displacement node, you'll find the change range option. And in here you can change to a new minimum or a new max, or you can adjust the old minimum and max. So for our circumstances right now, we actually need a -1 for a new minimum. And so what this will do is it'll allow the black to now influence in negative space downward. And so now if we look at our object, it's represented correctly. Now we're actually having a negative influence. Our gray is now mapped to the middle, and our white is pushing upward. And so this is something to keep in mind when doing displacement maps, that sometimes relative to the package the displacement map was created in, you sometimes have to remap the ranges into -1 and +1 so that you get the full range of positive and negative values pushing up and down your displacement map. And so that concludes this redshift displacement tutorial.